In today's video, we're going to talk about paper chromatography. We'll take a look at how it's done, explain the theory behind it, like what the mobile and stationary phases mean, and also show you how to calculate RF values. Now, chromatography is a general analytical technique used to separate the different substances in a mixture so that we can then identify them. And there are actually lots of different types of chromatography. But the one you need to know about is paper chromatography, which can be used to separate the different dyes in an ink. The first step is to take a piece of filter paper and use a pencil to draw a line near the bottom of the sheet, which we call our baseline. Next, you want to add your sample of ink, which you think might contain lots of different substances, to the pencil line. Then we need to find a beaker and fill it with a shallow amount of solvent, like water or ethanol. We are now ready to start, and we can place the filter paper into the solvent. But importantly, we have to make sure that we don't submerge our pencil line and our spot of ink, which is why we made our solvent shallow. And if you're being careful, you should really place a lid on top to stop the solvent from evaporating. Then we just wait for the solvent to seep up the paper, and as it does so, the different dyes that make up our ink will dissolve in the solvent and move up with it. What makes this interesting though, is that each of the different dyes will travel up the paper at different rates, and so they'll end up separating out, which tells us that each one must be a different substance. So we've basically separated out the different substances. However, if any of our chemicals aren't soluble in that solvent, then they won't be able to dissolve and move up the paper, so they'll just stay on the baseline. Once the solvent has almost reached the top of the paper, we take it out and leave it to dry, and the pattern of spots that we have left is called a chromatogram. Now, to explain why the different chemicals move up the filter paper at different rates, you need to use a couple of weird terms: the mobile phase and the stationary phase. What makes these things odd is you don't want to think of these phases as periods of time, but rather as types of substances. The mobile phase is a substance that the molecules can move in. It's always a liquid or a gas, and in our paper chromatography, it would be the solvent that we used. Meanwhile, the stationary phase is a substance or material that the molecules can't move in. So usually a solid, or sometimes a really thick liquid. But for us here, it would be our paper. During the chromatography experiment, the different chemicals in our sample of ink will constantly change between the mobile and stationary phases, dissolving in the solvent, moving a little bit, and then binding to the paper, over and over again. And so overall, how much time they spend in each of these two phases is going to determine how fast they move up the paper. With the chemicals that are more soluble in the solvent spending more time in the mobile phase, and therefore moving faster, and those that are less soluble, or are more attracted to the paper, spending more time in the stationary phase, and so moving more slowly. So if you think about it, how far each of the chemicals travels is dependent on the properties of that substance. And if we did the same experiment again, our chromatogram would look the same. This means that if we measure how far each substance moves, we can compare those values to a data book and identify which type of chemical it must have been. How far each of the chemicals moves, though, is also going to depend on how long we leave the experiment. So instead of comparing the actual distance, we instead calculate a ratio called the RF value, which is equal to the distance travelled by the substance divided by the distance travelled by the solvent. So if this pink substance had travelled 6 centimeters from the baseline, and the solvent had travelled 10 centimeters, then our RF value would be 6 divided by 10, so 0.6. One of the important things to appreciate with chromatography is that when we do chromatography with a pure substance, so a substance with only one type of chemical in it, then it won't separate out at all. We'll just get a single spot on our chromatogram, for which we can calculate a specific RF value. However, if we did the experiment again, with the same substance but a different solvent, or a different type of paper, then the chromatogram might look different. And our RF value would be different too, because we'd have changed the mobile or stationary phase. So when a chemist looks up an RF value in a databook, they'd have to take into account which solvent the experiment was done in,